right, line A1, learning task 19. We're going to go and talk about impedance. And we have very briefly, at the very beginning of this learning task, we started, or not this learning task, but this entire line that we have, the A1, we took a look through some trig, and then there was solve a couple of trig values. I think it was like the fourth or fifth learning task in, where we started to go and draw out those triangles, and we use that analogy of, what if you're biking up a hill? And, how does the gravity of the hill and how does the wind the headwind you're biking against, how does that both affect your performance? And we said, you can't really differentiate when you're on the bicycle. You just know that you have to go and overcome the vector sum of the wind blowing against you and the gravity that is pulling you straight downward. And we feel that as the overall force that we need to go and overcome. When we are dealing with impedance, impedance is going to be the same thing, where we are now going to start to look at what forms overall opposition. We've just, over the last couple of learning tasks, defined what reactance is. Capacitive reactance and inductive reactance are going to go and be when we get opposition caused by the electrostatic field or the electromagnetic field that is going to go and prevent us from having unrestricted current when we put one of those components, either the capacitor or inductor, onto the circuit. And we know that that thing is going to be either an XL or it is going to go and be an XC, one of those two, depending upon which one we pick. We know that we get that opposition, but we also know that it's impossible to build a circuit without any sort of copper wire, which is going to go and cause resistance. We're going to have other components inside there, contacts, components inside of our actual generation system, the panel lugs, everything inside of there has some form of resistance. So we are always going to have these systems that are going to go and have XL or XC, but they're also going to go and have a value of R, or resistance, as we would go and call that. Let's talk about the resistance, the physical resistance that's going to be dissipating heat, and that's how we differentiate it, is that all resistance dissipates heat somewhere. Dissipates heat. Gets useful work done. Heat is a useful conversion of electricity. I'm sitting right now in a minus, let me check the, it's a -4 garage right now, but I got a little electric heater down by my feet, so it's helping keep the edge off right now. Heat is going to be something that defines resistance. Resistive components dissipate heat. The XL or the XC, those are the reactive, the quadrature, the wattless, the useless power that we are going to go and have in our system. We use the analogy of the bank deposit withdrawal, deposit withdrawal, deposit withdrawal annoyance, right? Nothing effectively gets done by them, although they are active. They're just kind of doing busy work on the system itself. That's what defines them, is that they don't get anything done. They take and they give back, but at the end of the day, it's all a moot point. Overall, my system has to go and see an overall component that is made up of the true useful work it's doing plus the busy work that it's being required to do by the XL or the XC. Let's define the resistance first. First of all, we're dealing with resistance in AC. Now, we have talked about R in DC. Resistance in DC is equal to my K, the type of material, multiplied by my L, the length of the material, all over top of my CMA, the circular millet areas of that material. This defines it based upon the physical component that it actually is. But inside of an AC system, we have got all of our shred losses as well. Put those ones down here. I know we've defined them already once, but it's going to be my skin effect. Skin effect. Hysteresis. Radiation losses. Eddy current losses. And dielectric losses. Oh, we couldn't explain that one before. Now we can. These are all going to be AC losses that come off as heat. Skin effect is where I'm going to go and push all my electrons towards the outside of my conductor. There's more collisions, there's more heat that comes off. Hysteresis is the lagging effect on the magnetic domains, where they have to kind of break over and go in the one direction and then push over in the opposite direction. So it's going to give heat as well. It's pieces of iron, literal pieces of iron bending back and forth inside there. Radiation loss is where I lose a line of flux from a circuit, but then it goes out into the universe somewhere and cuts across somebody's glasses framed or across a swing set or something like that, and it induces a little bit of heat in there, right? EG is equal to BLV. We have moving lines of radiation. Eddy currents are going to be induced voltages. EG is equal to BLV. Once again, we've got flux lines that are going in and out, cutting across cores. We're going to set up eddy currents inside of a lot of our equipment. We laminate the equipment to try and prevent it, but it still happens. We can't get rid of them all. And the last one's going to be my dielectric losses in the insulation. We took a look at a cap, and we saw how we distort our dielectric, right? The center part, the nucleus, compared to the valence shells of the electrons are going to be in distortion. And it's still made out of a physical material. You can take a piece of plastic. If you bend a piece of plastic back and forth rapidly, that plastic will heat up and probably will eventually break as well. Same deal that we're dead. It's all heat. All of these things are eventually going to come off as heat somewhere. So what we do is we add them to our DC ohmic resistance, right? That K times L over the CMA. We've got what we have for our DC resistance. Then due to the fact that we have got AC, we get all the rest of these. All of these shred losses, by the way, are going to go up whenever we go and increase our frequency. This is why we don't have a lot of iron core components in high voltage or inside of high frequency applications. This is going to be our total resistance made up of all of these. Some of them we can measure with a meter, the true pure DC ohmic resistance. Other ones we can only get to through calculations, taking readings of voltage and current and then making the calculations to figure out what we have inside of there. Inductive reactance is going to be one of the other forms we can have, and it's going to be XL. And if we take a look at the XL, what we'll see is that usually the XL is going to be graphed against the R in the upward direction. Now, this is just convention. There's no mathematical reason for why XL has to graph up into the top over there. In fact, in a lot of cases, it would make more sense for it to graph down because we know that it's inductive. It's a lagging type of power that we have. But for whatever reason, it's been drawn upwards. Probably just due to the fact that most of the systems that we deal with are going to go and be inductive, and so we draw more of these triangles. And to be honest, I just feel better about an upwards facing triangle, and probably so does a lot of other people, and so that's just kind of why that convention has stuck. XC, no matter for how we develop the triangles, XC is going to be the opposite direction. This is highly critical. Note that my resistance is the same for both of these. It's along the x-axis, it's at 0 degrees. Because if I were to go and graph my resistive current, and we did this earlier on, we saw that my resistive current crosses through the x-axis at the exact same places as my voltage crosses through. It peaks at the same points, and it crosses through at the same point, which means it's 0 degrees out of phase. That's why we draw resistance always at 0 degrees. The XL is going to have to be 90 degrees out. The XC is also going to have to go and be 90 degrees out. So we'll draw them like that. Once again, just don't lose sleep over, which one of these is going to be facing up, which one of these is facing down. Pick a convention and stick with it. I suggest you pick the convention that is shown on this page because this is the one that I'm going to do. And if you decide that you're going to draw XC on the up and XL on the down, that's fine. You just got to remember that I'm doing it different and your way and my way will not always correspond then. So pick one, stick with it. Once we know the total amount of resistance and the total amount of either our XL or our XC that we have in a system, we can then go and figure out our total amount of Z impedance that we are going to go and get out of that system. And once we know that total amount of impedance, we can figure out this phase angle. Remember all that trig stuff that we covered off earlier? This is why we need that trig. We need to be able to figure out phase angles because when you take a look at these, oh my goodness, would you take a look right there across the center? We see angles that we are going to need to use in order to calculate types of power off of these. So we do need to be able to calculate that. Now, once again, we've got this lovely, lovely little sharp calculator that is able to go and do those. We can just pick our values. Let's give this resistance a value of 4. We'll give this XL a value of 3. We know that if we got a 3, 4, we should have a 5 for our hours over there. Let's just go through how those are added together. Once again, you're going to be in mode 3, so you got the little XY up top there, or the second RO, whichever you want to have. Both of them are the same angular mode, just one of them is going to give you polar, that's this one. The other one's going to give you XY. And if I want to add these two together, my X value, which is my resistance, and my Y value, I'm going to go and take the X value, I'm going to say 4, and I don't need to put it in at an angle, but I could. 4 plus, and then I'm going to go and say I3. Oh, hold on. Try that. 4 plus, I hit the wrong one there. It's this one. I3. And that's going to go and give me a result of 5. And if I want to know the angle, I just go second comma and it gives me 36.7 degrees, or 36.9 degrees. So that's one way that I can go and do it. Second function goes back to that one over there. The other way that we can go and do it with this calculator, and this calculator is lovely because now it's just given me that angle so I can use it for everything else. But the other lovely thing about this calculator is that I can just put them in at the angles. If I forget how to do that I thing, I can just say 4 angle 0 plus 3 angle 90, positive 90, right? And that would go and give me the same answer, 5 at an angle of 36.87. For this one, all I would need to do is I would have to have a negative 3, right? Because it's going in the opposite direction. When I do that, let's try that. 4 plus I negative 3 equals a value of 5 at an angle of negative 36.87. So just use the calculator to go and find these ones. You know, that we don't need to go and get all crazy with, you know, throwing in massive amounts of trig. All right, looking at this table then that we have over here, now what they've done is they have gone and broken it down into 4 columns over here. The first one's going to be DC values. This is going to be for my Ohm's law, for my Watt's law, and then for my derivatives down here at the bottom. The second column is going to go and be for AC impedance. Impedance is going to be across the wide side of our triangle, right? So if we go across here, if I want to know the impedance, I see it's the hypotenuse, and to talk about this now, they do say for series circuits only. We'll get to that later on when we do series parallel, why these are only for series circuits. But just know that there are some that are only for series circuits. See how it's Pythagoras that's for series circuit? If we can get away from using Pythagoras, there's a good chance that we're not going to get ourselves screwed up. But looking at my impedance, if I take a look at my total voltage over top of my impedance, it's just Ohm's law. I can find my current. I can go and find my total VA by taking, this is a very important one to us, note that my VA that I'm going to find, that's going to be the total amount of volt amperes, or my total amount of power delivered by the system, is just my E times my I. And if I want to go and take my line voltage times my line current and multiply it by cos theta, then that transfers my VA down into my resistance value that I'm going to go and have, my power that I'm going to have. And if I were to go and take my line voltage and current and multiply it by sine of the angle, then that would go and take me into my VARs of that system. We're going to do a lot of angular stuff in the next next module as we go through a bunch of power factor correction. For now, we're just going to go and take a look at calculating impedance. On your next page, they show a bunch of different components. I suggest that for every single one of those examples, that you draw that circuit. If you draw the circuit out and then try to solve it, it's usually going to be a little bit easier to see which components lie where. Place your Z's on the hypotenuse. Place your X's on that Y, your XLs and XCs, on your Y-axis, and place your resistance along that X-axis. All right, I'll leave you to those examples. Do go through them. Just because I'm not doing them on the video doesn't mean that you don't need to go through them. I'm just not doing them on the video because what's the point of me walking through the entire thing when it's so well laid out inside of there? So I'll leave you to that one. Cover those off, then cover off the self-test, and get any questions that you have resulting from all of this answered then in your follow-up Q&A to the session. Cheers.